Hi, I'm Ellie Leaders, the project manager for San Diego Science Alliance's Youth Space Institute. Now you might be wondering, what is San Diego Science Alliance's Youth Space Institute? I am here to tell you. It is a program dedicated to enabling a team of young high school-aged girls to send a fully functioning microlab experiment to the International Space Station. Now, while this sounds like a daunting task, we have dedicated mentors, generous beneficiaries, and an incredibly hardworking team, as you can see. Now, as an overview for our project, our microlab experiment is dedicated to finding a new substance to protect the International Space Station from particle radiation over long-term spaceflight. The substance we're using is neutron putty, and we're using two types of data collectors, quantitative and qualitative. The quantitative is an incidose dosimeter, which will be tracking each count of radiation that it comes in contact with, but we are also including films and a bariotrack tracking device that both of those will come in contact with the radiation and leave a different darkness for how strong it is. So not only will we have the number of instances of radiation, but we will also have the strength of the radiation we interact with. Now, the reason why we chose to do this is because of long-term spaceflight. If we want to send astronauts past the moon, if we want to really send them out into deeper space, we need something to protect them from long-term radiation. Currently, astronauts can only handle up to around 6 months of radiation up in space. Well, we want to help protect them for a longer period of time, so that way we can explore deeper into our universe. Our goal here is to find a new test a new type of blocking device that we could potentially use on these long-term space flights.
Hi, I'm Tess.
And I'm Natalie.
And we'll be telling you the hypothesis. We will put two incidose dosimeters in a 4-inch by 2-inch by 2-inch microlab on the International Space Station.
If one incidose dosimeter remains uncovered, while the other dosimeter is covered by the boron hydrocarbon putty, then the detector that is covered by the boron hydrocarbon putty will sense less radiation than the detector that remains uncovered, because the boron hydrocarbon putty is high in hydrogen, which helps to block neutron radiation because it can disperse the neutrons through elastic scattering.
We will also put 2 stacks of bariotrack solid-state track detectors in the microlab, which will track the radiation on a microscopic level, as well as 2 film dosimeters.
One stack and one film dosimeter will remain uncovered, while the other stack and film dosimeter will be covered by boronated hydrocarbon putty.
Oh, thank you.
Hi, my name is Emma Ling, and I was the head researcher for our team, and I mainly research space radiation. So there are 3 types. The first type is trapped radiation, which occurs under the Van Allen belts which surround Earth. So that's basically within our atmosphere there's radiation that's trapped, and that's mostly the radiation that we have on Earth. Then the second type of radiation is solar particle events, and this radiation occurs like once every 11 years when there are solar flares and like corona events that happen, and sunspots and all sorts of particle showers where the sun, there's explosions on the sun, and that creates a lot of radiation that gets sent our way. And then the third type of radiation are GCRs, which stands for galactic cosmic radiation. And these are like the constant streams of neutron particle radiation. These are the most harmful to humans because they rip apart our DNA when they collide with the molecules inside of our body, and that leads to cancer.
Hi, I'm Claire Kearney, and I'm the mechanical engineer, and I'm going to be explaining the structural layout of our experiment and some of the elements of what goes in it too. So since we have a very limited space, we're trying to maximize the amount of putty that we can put in it, and also maintain the maximum amount of similarity between the things that are covered in the putty and the things that aren't, so like our control and our experiment. So this is our structural layout approximately, and the incidose is our main dosimeter. which someone else is actually going to be explaining in more detail later. But it kind of looks a little bit like a flash drive, and it's about the same size too. And then above that, we're going to have a piece of film that will read the radiation and give you the amount of rads that it receives during the entire experiment. And underneath that are these little lines, which represent the baryon track crystals, which are little rectangles, and when charged particles hit them, they leave an etching, and so when you get them back after the experiment, you can put them under an electron microscope, and you can see which type of charged particle hit it at which area, so we can tell the amounts of the different types of charged particles that it experienced in space. And so you can see that the bottom half of it is what's covered in the putty. And the putty is a boron-nated polycarbon putty, which has about 10% boron and a high hydrogen content, which has been proven to help reduce the amount of charged particles, especially neutrons, that go through it. And because it has a low atomic number, it's not going to cause as much of a subparticle shower as something with a higher atomic number would, like lead.
Hi, my name is Lady Sarah Federico. I'm the dosimeter technician. I'm working with the Incidose sensor, as you can see right here. It's a radiation sensor, which is located within this thumb drive. Pulls out. Basically, we're going to have two of these within our project. One will be a control, and one will be separate, covered in boronated hydrocarbon putty. And these read particle events for radiation that happens in space, and it measures radiation levels in millirems. It requires initialization from software that we have installed on our computers, and basically when we plug it in, it gives out a status report of the radiation that was picked up, and it's cumulative data, so it gives a graph of the radiation levels compared to the danger levels, and so it'll tell us whether or not the radiation that was picked up is in a healthy area, or if it's too dangerous for the astronauts who are exposed to it. And basically what we're trying to see is if the boronated hydrocarbon putty is enough to block out any radiation from it. And when we get the thumb drives back from the International Space Station, then we'll be able to compare the data and see if our hypothesis was correct.